is home to one of the largest sago industries in the world. Every year, millions of tons of sago are processed into starch, an important food and industrial ingredient. Producing sago starch is a labor-intensive process. The pith is washed and separated, extracting valuable starch for various applications. But after the starch is removed, most of the material becomes waste. In fact, more than 2/3 of the sago trunk is discarded. For decades, this biomass has remained underutilized. But what if this waste is actually a valuable resource? In drilling operations, fluids must maintain stability under extreme conditions. Without proper viscosity, wellbore collapse can occur. Polymers are essential to ensure performance. Xanthan gum is widely used for this purpose. However, it is typically produced from food-based sources such as corn and tapioca. This creates a growing conflict between industrial demand and food supply. And so the challenge becomes clear. Can we produce high-performing xanthan gum without relying on food crops? Sago biomass contains structural carbohydrates that can be converted into fermentable sugars through a series of biorefinery processes. The process begins with biomass preparation, including size reduction and pre-treatment to break down the lignocellulosic structure. This is followed by hydrolysis, where complex carbohydrates are converted into simple sugars. These sugars are then utilized in fermentation by Xanthomonas campestris, producing xanthan gum. Finally, the product is recovered and purified to obtain industrial-grade polymer. This integrated process transforms agricultural waste into a functional industrial material. The produced xanthan gum exhibits strong shear thinning behavior. It remains viscous at low movement and flows easily under shear, a key requirement for drilling fluid stability. This approach reduces waste, lowers dependence on food-based feedstocks, and creates new value from biomass resources using the developed bioprocess and recovery. This innovation delivers value across people, planet, and the industry. While scale-up remains a challenge, strong performance and growing demand highlight significant industrial potential. This pathway demonstrates how low-value waste can be transformed into high-value industrial material. This life cycle begins with sago biomass, an abundant agricultural residue. Through pre-treatment and hydrolysis, it is converted into fermentable sugars. These sugars are then used in fermentation to produce xanthan gum. The product is recovered and applied in drilling fluids. This pathway demonstrates how waste can be transformed into a valuable industrial material. The technology has been validated at laboratory scale with research outputs, awards, and ongoing intellectual property development. The next step is scaling from 1 liter to 10-liter systems towards an efficient and economical process design. What was once considered waste may soon become a strategic industrial solution. BioPol X, engineered for performance, built for the industry.